something. Okay, so today what we're going to talk about is the lecture that was on Monday, the online lecture on Monday, which is going to talk about work and kinetic energy and potential energy. And these ideas are something that you've already dealt with, and so we're probably going to spend today about 40 minutes, 35 or 40 minutes talking about things. I'll let you loose. But let's just first talk about kinetic energy. And we write delta KE. Now, whenever we say delta, delta is saying we're looking at state 2 minus state 1. Always state 2 minus state 1. And so we write this equation 1/2 mass times velocity 2 squared minus velocity 1 squared. Pretty simple and easy. It's a plug and chug type thing, really. But I want you to pay attention to its units, and so that's why I'm going to also bring up potential energy. In fact, you'll hear it called gravitational potential energy, because we are looking at the potential energy caused by gravity, not by a spring or anything else, gravity. And so we're going to say again, delta PE. Delta means it's a property. We're going to look at it at state 2 and subtract it from state 1. Mass times the gravitational pull times Z2 minus Z1. Okay, that's what we're going to be looking at. Now, potential energy is a property, kinetic energy is a property. We don't need to know how they go from state 2 to state 1. We just need to know they're there. It's a storage of energy. Those are things you need to know. But also what we have to remember is the units here. We can't just plug and chug. It's plug and chug and check units. So what we're often going to see in SI is that this calculation is going to give us units of joules. Our homework problems, our problems in this class often are going to be in the scale of kilojoules. So you're going to have to divide by 1,000 to get into kilojoules. Every time you do a problem with this in English units, it's going to be, you have to have a conversion, every time. Okay, so I just want to, this is probably the first issue. We also talked about the idea of work. And in thermodynamics, there's going to be really 3 types of work that are going to be predominant. And I'm going to talk about those 3 types of work today. So the first type is, let's just say we have a container. This is just a box, a tank, something. It's closed, it's rigid container. Okay, now what I'm going to put in here is I'm going to put in a paddle wheel or a mixer, and I'm going to turn that mixer, and I'm going to add work to that system. I'm going to beat up or mix up the air. Okay, remember what we said about work in the lecture. This is the first rule of thermodynamics that we really did. Work from the surroundings to the system is negative. Work from the system to the surrounding is positive. Thermodynamically, that's what we consider that. It's a huge thing. We got to understand that. That's very, very important. I'll say it again. Work from the surroundings to the system is negative. Work from the system to the surroundings is positive. But when we are adding work to the system, we are adding energy to the system. So physically, reality says we're adding energy to the system. That should be positive. When we're taking work out of the system, we're removing energy from the system. That should be negative. That's opposite of how we've set our sign convention. So we have to write this equation minus the summation of the work is equal to delta KE plus delta PE. Okay, and we put the thermodynamic sign convention inside the parentheses. I always put a parentheses around that because it helps me understand. Inside the parentheses goes the sign convention, and then I act on it with that global negative. Okay, back to our example problem here. I have a paddle wheel that I'm spinning and beating up the air. Is that, or if I say 10 kilojoules of paddle wheel work, is that positive or negative? Negative in thermodynamic convention, yes. Negative. We're going to talk in thermodynamics in this room, so we'll talk in thermodynamics. It's negative. Okay. So I'm going to say this will be minus a minus, let's say minus 10 kilojoules. Okay, same thing if it was 5 BTUs, it would be minus a minus 5 BTUs. Okay, that's what we're saying. Another type of work that you might see. Oh, I should have drawn my system out here. I didn't really draw. I kind of got sloppy here. There should be a system here. The system is going to be my liquid or air or whatever it is. Okay, let's draw another system. We might have a resistor inside our tank. So resistor, what happens is you apply electric current to it, you plug it in, it heats up. But we don't care. In the way I've drawn the system, this dashed line that I've drawn on here, we don't care about what that it's a resistor. It could be a pencil sharpener. It could be an Xbox or a Nintendo Switch. Okay, it could be, I don't know, what do you plug in? What do you have that how should you plug in? I don't know. Your refrigerator. That's the only thing I can think of. Pencil sharpener, Xbox, and a refrigerator. That's where we go. I don't give a damn. I don't care. Okay? All I care about when I draw those dashed lines is what do I see crossing the boundary? And what I see crossing the boundary is electrons. The system doesn't tell me anything about what's happening inside there. All I have to know what is crossing that boundary. Electrons, and that's going to be electrical work. Some type of electrical work is passing through the system. And again, it's coming from the surroundings to the system, so it'll be negative electrical work. That's another thing we'll deal with. But the primary mode of work that we're going to have is going to be because of a piston cylinder, because this piston is moving up or down and changing the size of our boundary here. We have boundary work. And boundary work can be the integral of P dV. We talked about that from 1 to 2. If we're expanding, what's happening is the piston, the gas inside the piston is working on the surroundings. That's going to be positive boundary work. If we have compression, the surroundings are working on the system. There's going to be negative boundary work. And this equation gets the sign convention out without question. So when I go up here and I write this summation of all the work in the parentheses, it could be that there's 3 types of work. It could be there's a paddle wheel, there's electrical resistor, and that there's a boundary moving. It could all 3 we could put in there, and we have to put them in each one of those in there with the appropriate sign. Now the purpose of this in-class portion is to go over these ideas, and then what I also want to do is I want to attack what I would consider the hardest homework problem, and give you some tips and tricks about the hardest homework problem. Okay, so this is kind of a little, what do we have, an 8-minute review about what we talked about in the lecture. Any questions about that? Okay, now let's move on. Let's talk about the quote-unquote hardest homework problem. Okay, and the hardest homework problem, I believe, is going to be this problem that has an incline, and you have a can on this incline, a can of soda, and this can of soda has a mass, it's equal to 0.4 kilograms. Now, that was in my numbers. You might have a different thing here. Okay, and that's going to be my system. So I'm just going to highlight this. This is my system. This is my purple highlight. This is my system that I'm working with. And they tell me it moves down a surface inclined, in my problem, was 20 degrees. And it's acted on by a constant force. So there's a force acting on here that they call R, and R is equal to, in my case, 0.05 newtons. And they say there's no friction between the can and the inclined surface. They want to know about the change of kinetic energy of that can. If it drops a distance here of 1.5 meters. So it's going to slide down this incline, but it's eventually the center of mass of that can is going to go down 1.5 meters. Now, the book has a solution for this problem. That's, I think, much more complicated than what they need to be doing. In fact, they treat this problem like a dynamics problem. And that's okay. Dynamics and thermo are the same. We deal with the same equations. We're saying we may call things differently, but it's the same stuff. But since we're in thermo, I think, why don't we handle this with thermodynamics? Okay, so what I'm going to do is first thing I'm going to do is I'm going to write down the equation that I have. Minus the summation of all the work is equal to the change in kinetic energy plus the change in potential energy. Well, the problem statement says, what is the change in kinetic energy? And so my initial thing is, well, the easiest way to do that would be, say, 1/2 mv2 squared minus v1 squared. But I was not given any velocities in my problem. It wasn't given to me. So that's not the first avenue I want to go down. But if I look at this equation that I'm provided here, I know, well, I could probably solve for the work because there's a force acting on this can, moving it through a distance. And I know some information about the potential energy change. I could solve for everything but kinetic energy and then basically solve for kinetic energy. So there's going to always be a couple different ways to solve problems in this class. Either directly solve for it or solve for everything else in the equation and find that missing the unknown. Okay, so in this situation, we're going to find the unknown. Okay, let's talk about our work. Here, we're not dealing with pressures or area. We're dealing with that integral of f dx. Okay, f dx. So the force here is r. It's a constant force. What is our dx? The distance it travels, and you're doing this down the incline, right? So we're going to be going from this point here to this point here. This is point 1, and this is point 2. We want to find out what that distance is. Can we find that distance? Yeah, we know how far it drops. And again, I'm kind of mixing up here because maybe I'm saying that the center of gravity, so we're going from here to here, whatever, here to here. We're going to have a triangle that's 20 degrees, 1.5. We can figure out what this unknown is. That's trig. We know that. Okay? If we find r times dx, in this case will be, if we go from 1 to 2, it's going to be x2 minus x1. If we call x1 our 0 location, this is just going to be r times x, or s, or p, whatever you want to call that distance down there. That's the force times the distance. Now, the integral of f dx, if we make our coordinate system so that maybe this is our positive, that force is acting opposite of the positive. Okay? And so we could say it's negative. Or if we make our coordinate system like this, now r is going in the direction of our coordinate system. And we say, okay, that's positive. I don't care about our coordinate system. What I'm caring about is thermodynamically, what goes into that parentheses is going to be the thermodynamic sign convention. So what I'm going to ask you is this work, Rx, is it positive or negative thermodynamically? Negative, why? It's the surroundings are acting on the system. There's some force outside acting on the system. So I need to put a negative number here, and then I'm going to put this negative sign here. Okay, I'm going to work this thermodynamically. This is the only time that you're really going to deal with f dx. Starting the homework that I assigned today, it's all going to be PDV. Okay, we're not going to, forces and distances are more dynamics. We're going to deal with thermo, so this is kind of the only time you're going to be dealing with that. Okay, so that we can figure out that. We don't know the kinetic energy. The potential energy is just mass times the gravity times z2 minus z1. Again, I have to here I have to think what's happening. It's dropping 1.5 meters. So x1, I'm going to call my datum, I'm going to call it 0. What is x2? negative 1.5. We're going down 1.5. We're losing potential energy. Okay, and that's what I put in there. Now, what are some common issues with this problem? Well, first of all, it's not getting the signs right. I think right now we're in the thing, it's getting those signs right is going to be the important stuff. Getting the thermodynamic sign right for work, and then thinking about your kinetic energy and potential energy. Is it a loss or is it a gain? That's what you have to figure out. The second thing that happens, a lot of students will go over here to this side of the equation with F dx, and they'll say, well, there's two forces acting on it. The problem statement said there's two forces. There's acted on by a constant force R and the force of gravity. They'll say, great, there are two forces acting on it, and so they'll put both forces over here in this equation, and they'll integrate it, and then they'll also put potential energy here. That's where I think it's important that you understand the derivation of this, because remember, in the derivation of this, we said, hey, there's all these forces, but we're going to specifically pull off the gravity force and put it over here and make it special and call it potential energy. So because of that, this F dx this is all of the external forces acting on it. So that's important for us to know. So the two common errors here are going to be doubling up the potential energy and messing up the signs. Usually they have the numbers right, but the signs are wrong. It's important that you start gaining some understanding of the equations and also not just plug and chug, but also understand what's it mean. I'm losing potential energy. The force is coming from the surroundings, what all that means. All right, is there any questions about this problem? Okay, I have another problem for you today. This is a different problem. This is a thermo problem. Okay, this problem says carbon dioxide gas is in a piston cylinder assembly. So I'm going to draw a piston cylinder here. And it's going to have carbon dioxide gas inside of it, and that's going to be my system. And it tells me it undergoes a process from a state where the pressure and volume is such and such to a pressure where to a state where the pressure and volume is such and such. So here's what I'm going to tell you. State 1, they told me that the pressure at state 1 is equal to 5 psi, and the volume at state 1 is equal to 2.5 cubic feet. And they told me to go to state 2, where the pressure at state 2 is equal to 20 psi, and the volume at state 2 is equal to 0.5 feet cubed. Okay, those are our two states. There's a process between those two states. We're given some properties inside of each state. Now you should be able to right now look at this and tell me what's happening. Okay, I'm going from a low pressure to a high pressure. I'm going from a bigger volume to a smaller volume. Pressure's going up, volume's going down. Picture that in your head. It's compression. We're compressing that carbon dioxide, which means that the work is going to be thermodynamically positive or negative. We are compressing it. Or negative. The surroundings are acting on the system, causing that to be compressed. So I know right away my answer should be negative. If my answer is not negative, I've done something wrong. Whenever I have compression, my boundary work is negative. That's what I should always think. Okay, now, they have told us that the relationship between the pressure and volume in the process is that the pressure is equal to 23.75 minus 7.5 times the volume. If you look at that, that relationship is linear. You learned the equation of a line is y is equal to mx plus b. This is p is equal to mv plus b, or however you considered the line in whenever you learned it. So this is a linear relationship. And they didn't give us any units for this. Okay, so I'm going to give you the units of this because this is units of pressure here, right? So this has to have units of this first term. I'll rewrite it with the units here. Pressure is going to be equal to 23.75 pounds force per inch squared minus 7.5 pounds force per inch squared per foot cubed. Okay? It's got to be because I have to take a volume times this number, which is have units of feet cubed. It's going to cancel out feet cubed, and I'm going to have PSI and PSI together. Okay, so we have to think about what the units would be. They don't give them to us. They don't worry about it. So the next thing I'm going to do is I'm going to go up here and I'm going to draw a picture of this situation. I'm going to draw a pressure PV diagram. Okay, so I'm going to say my two pressures I'm dealing with are 20 PSI and 5 PSI. This is in PSI. Oops, here we go. PSI. And our volumes are going to be 0.5 and 2.5 cubic feet. And so where's my point 1? My point 1 is 5, 2.5. Here's my point 1. My point 2 is 0.5, 20. Here's my point 2, and there's a straight line between these two. I'll draw it the right way. I'm going this direction. Here we go. That is our process. Straight line. I can't assume it's a straight line. I was given the information that's a straight line. They want me to find out how much work in BTU for this situation. We know it's from the surroundings on the system. We know it should be negative. When we're looking at work in a situation like this is our boundary work, so we say work is equal to the integral from 1 to 2 of P dV. That's our equation. Okay? Well, we're going to substitute in here from 1 to 2. Our pressure is going to be 23.75 minus 7.5 times my volume dV. And this is where those 3 semesters of calculus are going to pay off. It's prerequisite for this class because you need to be able to do this integral. And I think you can. No integration by parts or U substitution or any of that stuff, just this. This is probably what you need to know how to do. And so let's integrate that. We're going to get, this is going to be 23.75 times our volume minus 7.5 times our volume squared all over 2. Okay? Now, when we want to now do this, we're going to put in our volumes, and so this is going to be, we're going to evaluate this between state 1 and state 2. Okay, and so we're going to have work is equal to 23.75 times volume 2 minus volume 1 minus 7.5 times volume 2 squared minus volume 1 squared divided by 2. Okay, so we plug this in here, we're going to get work is equal to 23.75, volume 2, 0.5, volume 1 is 2.5. Okay, minus here 7.5, volume 2 is 0.5 squared minus volume 1, which is 2.5 squared, all over 2. Okay, so now we're going to do that calculation. Get out my calculator. Now let me make sure, I should probably make sure my units, I'll make sure my units here in a second. We'll look at my units. I should put units on everything, but I didn't. I skipped a step. It's going to be painful here in a minute if I don't get my units right. So work is going to be equal to 23.75 times 0.5 minus 2.5. Okay, this is going to be negative 47.5. And so what are my units here going to be? This has units of pounds force per inch squared, and this has units of feet cubed. So this is going to be pounds force feet cubed all over inch squared. Okay? And the second one is going to be 7.5 times 0.5 squared minus 2.5 squared divided by 2. I get that that's going to be a negative 22.5. And so my units here are going to be pounds force per inch squared per foot cubed times foot cubed squared. Is that right? Did I mess anything up yet? Okay. And so really what's going to happen here, this foot cube is going to cancel with one of these foot cubes, and I'm going to have the same units in both of those, right? I'm going to have the same units in both of those. That's important. We can't add or subtract two things when they don't have the same units. So this is going to give me minus 47.5 plus 22.5. I'm going to get negative 25 pound force feet cubed per inch squared. Okay, that's not my final answer. If I gave this on a test, I will guarantee that probably 30% of the class would give me that as a final answer, but that's not units of BTUs. So I know BTUs has foot-pounds in it. Okay, so the first thing I want to do is I want to get rid of these inches. So I'm going to say 144 inches squared is in 1 cubic foot. Yeah, in 1 cubic foot, in 1 square foot. And so that gets rid of our inches, it gets rid of some of our feet, and now I have pounds force feet. And now I'm going to look here and say, well, I know that 778 pounds force feet is in 1 BTU. Okay, so if I take 25 times 144 divided by 778, I get a number. That's negative 4.63 BTUs. Okay, that's my final answer. This problem isn't really a hard problem. It has some things in it, but units, man, units will really get to you. Make sure you follow your units. I got a little sloppy here. I was going without my units. Not what I'm trying to tell you to do. Make sure you get your units right. Now, that's the hard way to solve the problem. What's the easy way? Can somebody look up here and tell me what's the easy way to solve the problem? Easier way. What is, did you have something? Can you solve it graphically by the area under the curve? Absolutely. The integral here, integral PDV, is the area under the curve. So what I can do is I can draw this and find out what this area is. I can do it one of two ways. I could break it into a triangle and a rectangle, or I could say that is equivalent to, let me get a different color here that you could see. It's equivalent to a box that's like this, because this positive area would replicate that area there. That's how I like to do it, but I don't care how you do it. And so let's just see if we did it this way graphically, what would be the answer? And that would be work is going to be here. I would have to find the average pressure. So this is going to be P2 plus P1 over 2 times V2 minus V1. Okay? So what do we have here? Pressure 2 was 20 psi. Pressure 1 is 5 psi. Divide that by 2. This is going to be in pounds force per inch squared. My volume 2 is 0.5. My volume 1 is 2.5. This is in feet cubed. I still have to do my conversions here and say 144 inches squared is in 1 foot squared, and then 778 foot-pounds is in 1 BTU. And I'll make sure this all cancels. Inches cancel. One of my feet is remaining. Pounds, force, feet, they all go away like I expect it to. And if I do this calculation, I'm going to get negative 4.63 BTUs. So there's not always one way to solve a thermo problem. Graphically is how I probably would see this graphically first, is what I would do. Okay, sometimes when you're looking at the area under the curve, the area is positive. You might say it's V1 minus V2 or something like that. You have to also understand, okay, I have to think about which direction this thing's moving. Okay? Area under the curve will only work when you have straight lines. Flat line or a straight angled line. If it's a curve, you got to do the integral. Okay? Questions on this problem? All right. I have one more thing to show you today, and then we'll let you loose. If you understood what we're doing here today, I want to gain that you're not just plugging and chugging equations. If you start plugging and chugging equations in this class, you can be successful, but I think that the best thing to possibly do is to understand why and how and really get into depth, and that will help the other subjects become much easier when you fully understand one subject. Okay, if I go to Canvas, and I just want to pull up some of the resources you have here. If you go down to the chapter material, we're in chapter 2.2, broadening our understanding of work. All of chapter 2 is open. I just want to show you some things here. They have this learning hub that pulls up, and it says learning objectives. When you're studying for an exam, you should be able to go through these learning objectives and say, okay, I know those things. If you don't know those things, we need to go back and watch a lecture, read a chapter in the book. Okay? It's going to show you if there's what kind of content's available. There may be videos. The book may have, they were going to hire professors to help solve problems. They tried to hire me, and I said no. I didn't want to do it. I had performance anxiety. I didn't want to be out there and somebody watching me. So you won't see me, you'll see somebody else. But there's some animations that they're here. So we can see some of the animations. Here's just showing a constant pressure process, how that looks, how that would look on a PV diagram. Shows a constant volume process. And then it'll show a constant temperature process and how that line curves as we're going. Okay, maybe straightforward, simple, you may not need this, but there's going to be these options throughout the semester, throughout the chapter. It may be something that you want to look at, you want to explore. So there's going to be those. Okay. There's also going to be a summary down here. This is the TLDR. Too long, didn't read the chapter. Okay. I was saying in the 8:30, it's the TLDPA. Too long, didn't pay attention. TB, too boring, didn't pay attention. Okay, if you understand this is kind of really what you need to get from that reading of that chapter. They also have some, you can explore, you can go into this is all the resources that they have in the course, and you can see there's some course videos here. If we select chapter 2, there's about 5 videos here. We're not to them yet. They would show up in our learning hub if we needed them. There's the reference tables and everything like that. You can access the book in Learning Hub. You can access the e-text if you want to. But there's also some practice problems, okay? And so usually this is going to be called the check your understanding practice problems. A good thing also to make sure that you know what's going on. So it's going to say things like this: a process during which the departure from thermodynamic equilibrium is at most infinitesimal is called a blank problem, process. Do you know the answer? You say it's quasi-equilibrium. Yes, quasi-equilibrium, quasi-static. I understand what you're trying to say there. Quasi-equilibrium processes. Submit the answer, say you're correct. Not any points, you can get it wrong, no big deal, but it's a way to check to see what you're going. You can go to the next problem here. Kinetic and gravitational potential energies of a closed system, are they intensive or extensive properties? How many people say intensive? How many people say extensive? How many people just don't want to raise their hand? I was with you. I never raised my hand a single time in class. Never did. I sat way up there in the corner and didn't raise my hand. Remember, intensive can be found at a point. Extensive, you need to know something about the extent of a system. Because kinetic and potential energy need the mass, they need to know the extent of a system. So this is going to be an extensive property. Okay. When work is done on a system, what is transferred or stored in the system? Energy. Okay. So we can go through these things and we can answer these questions. Some of these questions are of this because we split section 2.2 into 2 lectures. Some of those we're talking about today in the online lecture. Okay, so I want you to know about these resources. You don't have to use them. I think you can get by on lectures alone in this class. My lectures are supposed to be that way. I intend them to be that way. But I want you to know about these resources. Okay, are there any other questions for me before I let you go? Any questions for me about this chapter, about this class? Anything I can help you with? Questions about life? Love? Nothing? You got it all figured out? Good. Maybe I should sit in your lecture because I don't have anything figured out. All right, you're free to go. I will see you on Friday, maybe, and we'll go from there.